All right, problem number 11 in group theory. We have let n be a positive integer, let g be a finite group with an odd number of elements, and let phi go from Sn to g be a homomorphism. Prove that phi must be trivial, i.e. phi of some permutation is equal to the identity for all permutations. Okay, so the first thing we want to do is we want to remark that every permutation in Sn can be written as the product of transpositions. For example, like the permutation 1, 2, 3 can be written as 1, 3 times 1, 2. Okay, and you could do that with any transposition you want, any permutation. Okay, remark that every permutation in Sn can be written as the product of transpositions, and observe that for a transposition in Sn, we have that the identity is equal to phi of the identity, which is equal to phi of that transposition squared, which is equal to phi of that transposition quantity squared, because we have a homomorphism. And let me spell out this this property first. Observe that for A, B, and Sn, or maybe this is fine. We'll go since phi is a homomorphism. Since phi is a homomorphism, hence the order of phi of just any transposition is less than or equal, well, I'll say actually it divides 2. It's the order it divides 2, and since G has an odd number of elements by Lagrange, the order of any transposition, missing a parenthesis, has to equal 1. Because the only divisors of 2 are 1 and 2, it can't be 2, because Lagrange says that it has to divide the order of G, but the order of G is odd, hence it has to be 1. Thus, the only element of order 1 is the identity for all A, B in Sn. Okay, but we want to have this for every, we want to have this property for every permutation, not just transpositions. So let sigma equal the product of n transpositions. Let sigma equal the product of n transpositions, where each is a transposition. Then, since phi is a homomorphism, we have that phi of sigma is equal to phi of tau 1 to tau n, which is equal to phi of tau 1 dots phi of tau n, which is equal to identity times the identity, which equals the identity. Okay, so since very first thing we said is we marked that every permutation in Sn can be written as the product of transpositions, we use that here and we write our general permutation from Sn as a product of transpositions. Then, since phi is a homomorphism, what we can do is we can separate each transposition, and then, as we showed earlier, phi of a transposition will just be the identity, and the product of a bunch of identities is just the identity. Hence, we've proved the claim.